Welcome to the third tutorial video for the Johns Hopkins Final Project Walkthrough. This video, we're going to focus on the needs analysis phase within the conceptual development stage. We're going to discuss the needs analysis inputs and outputs at each of the steps in the systems engineering process that takes place during needs analysis. These are operations analysis, functional analysis, feasibility definition, and finally, needs validation. Inside of operations analysis, I will be developing my concept of operations, my context diagram, and my objectives hierarchy. Throughout, I will be demonstrating how to apply each of these by using CORE. The needs analysis phase will provide the information we need to develop our concept paper and proposal for the final project. In the past, most students have skipped performing these systems engineering steps or entering any of their data into CORE, and they ended up confused when they finally started actually performing the systems engineering process. This set of videos will set the record straight. The systems engineering process is iterative and takes place at least once during each phase in the systems engineering lifecycle. Recall from your previous courses, the systems engineering lifecycle that Johns Hopkins uses is composed of 3 stages: concept development stage, engineering development stage, and the post-development stage. Each stage is composed of various phases. During the concept development stage, there are 3 phases: needs analysis, concept exploration, and concept definition. You will be performing the systems engineering process at least once during each of these phases. It is the concept development stage that you will be using throughout your project. The engineering development and the post-development stages would be follow-on activities from your project. You will notice that the outputs from concept development are your system functional specification and a defined system concept. These 2 deliverables are expressed in your A specification and your system architecture. These videos will walk you through these 3 phases and how I applied them to my final project. Let's take a look at what goes on during needs analysis next. As you learned in your concept development course, the primary purpose of needs analysis is to validate that the potential market exists for your concept and that the approach is feasible. That is, it serves to meet a need at an affordable cost that will provide a return on investment for potential owners, as well as at an acceptable level of risk. So the detail necessary to conduct needs analysis depends on the level of detail needed to make a convincing argument that your concept is in fact feasible. The inputs to needs analysis are the same as the inputs to the concept development stage, which are also the same as the inputs to the entire systems engineering lifecycle. The first is operational deficiencies in an existing system, and the second is technological opportunities that may be used to improve quality of life, replace existing technologies, or perform a function that was previously unachievable. Indeed, the initiation of the development of something new typically stems from the identification of a deficiency in an existing system that can be met by inserting your concept or an idea based on some new technology that could be used or exploited to serve a specific need. So you may have heard of these inputs as needs pull or technology push, but they are synonymous for our conversation. The outputs from needs analysis are estimates of the operational effectiveness of your system that will demonstrate what outcomes your new system will provide to meet the need, as well as a set of capabilities that your system will provide based on the studies you will conduct throughout needs analysis. For your Johns Hopkins project, you will require some research, serious thought, and consideration for the feasibility of your concept. You should include the time required to conduct this analysis in your project schedule. When you perform needs analysis, you begin with the inputs we just discussed and enter the systems engineering process. As I stated in my first video, the SD-PNP textbook tailors each step of the systems engineering process and gives them unique names throughout each phase. For the needs analysis phase, requirements analysis is also called operations analysis. Functional analysis is the same name. Physical definition is called feasibility definition, and design validation is called needs validation. The activities for each of these steps are outlined in detail in Chapter 6 of SEP&P, and I will be applying each of these in my own project. When we perform operations analysis, we will conduct 2 primary activities. We will first analyze the projected needs and then define the operational approach. The outcome we are after are a set of operational objectives that we will then translate into a formal and quantitative set of operational requirements further along in the systems engineering process. If we are replacing or improving a pre-existing system, it will come with its own set of constraints and must be taken into account from the very beginning. It's also important to think about the capability you're bringing to the existing system and how it meets the initial need. If a new technology is being inserted, that new technology also comes with its own set of constraints, which must also be taken into account. For example, attempting to integrate some new sensor technology into a satellite when that technology has only been demonstrated in a laboratory environment and was not designed for use in the extremes of space. I also want to point out that there are two inputs to operations analysis that comes from further processes downstream. The first one is a check on the functions from the next step, functional analysis. This basically means take a look at the functions and ask yourself if a set of functions meets the projected needs. If not, reanalyze the functions or reanalyze the projected need. If yes, proceed to the next step in the systems engineering process. The second one is the concept from the last step, needs validation. This is to validate that the concepts meet the projected needs. If it does not, then start here again and repeat the systems engineering process. This is what is meant when we say that the systems engineering process is iterative. If it does meet the projected needs, then the concept can be said to be validated, and you may proceed to the next phase in the concept development stage, which is concept exploration. We will talk more in detail about these and those particular steps. So let's bring my project into the picture and talk about analyzing the projected needs and proceed from there. It began on a cold wintry day as I pulled into a gas station to refuel my vehicle. As I sat shivering while refueling, I thought to myself, wouldn't it be great if I could stay in my car the entire time? I know what you're thinking, first world problems. But that was just me, and this capability can be extended to people that have a hard time exiting their vehicles, such as the physically handicapped, or in high crime areas where people are worried about exiting their vehicles. Of course, living in a state where gas station attendants are not required by law, my mind went to automating this capability. Simply stated, a driver pulls into the gas station, and the gas station refuels my vehicle in some kind of automated manner. Many ideas for how to do this popped into my head. However, it's very important not to dive too deeply into any specific solutions, only to know that there are one or more higher-level options available to you for you to analyze and illuminate, or what's called in the industry to down-select, to a couple of primary feasible ideas. Notice how the car disappeared inside my system. I didn't describe what's going on inside the system, only that it's providing autonomous refueling. So a vehicle enters my system, and my system refuels it without the driver having to exit the vehicle. That's it. Of course, there are many constraints I need to take into account, such as complying with local and federal regulations, as well as considering safety and return on investment. But the bottom line is, that's what I'm after. As shown on Table 6.1 of the SE P&P textbook, we want to have a general idea of how this problem could be solved, because if we had to break down the laws of physics or invent an incredibly advanced piece of technology to make it work, it may not be worth the time and effort we're about to put into it. However, we don't want to dive into specific solutions and stick to those the entire time. Instead, we simply want to gain an understanding that this problem can be solved with available technology or with a little bit of research and development. This requires that we perform some level of market research in order for us to determine that this is initially an idea worth pursuing. We will also want to conduct interviews with potential owners and users of this type of system in order to gauge their level of interest. When I did my project, I interviewed a couple of different gas station owners, as well as immediate family and friends for their input. I also consulted with a couple of experts in the robotics industry. Ultimately, most of the requirements will become requirements that I will have to address in my system's architecture. So I will use feedback from potential stakeholders as well as my own initial problem identified to write an initial need statement to guide me through the rest of this process. My need statement is that the automated gas pump system needs to provide a cost-effective service to gas station customers that is a convenient, safe, reliable, and secure 24-hour access to fuel without the vehicle occupants having to exit the vehicle during the entire process. The AGP system shall provide a number of the most common refueling transaction types and fuel types without involvement of gas station and banking personnel. The AGP system shall continue to provide these services in extreme weather. The AGP system may optionally provide ATM services during refueling transactions. For the automated gas station, there are several approaches, one of which could be something akin to any automated car wash. A vehicle pulls into a garage-like area where different machines will perform different functions, much like an assembly line, either moving around the car or the car moving around them. An even simpler solution could be that this garage is heated and contains a normal gas pump, so the occupants can get out of their vehicle and fuel them as normal. This solves the problem of avoiding the elements, which was the origination of my idea. This also is not technically an automated process, and that's fine. I was simply thinking of various ways to avoid being in the elements as I was refueling my vehicle. But as I mentioned, we expanded the market where the handicapped may be able to take advantage of this capability. No matter what the elements are outside, they are still incapable or have a hard time exiting the vehicle to refuel it. Simply hiring a gas station attendant would also meet these requirements. This will drive me to perform some kind of business case to compare the two alternatives throughout the life cycle. A detailed business case is beyond the scope of this project. However, you will have to come to the table with at least having thought about your concept from a life cycle cost and a return on investment perspective. So let's get back to this. Another approach could be pulling up next to a gas pump and a refueling device comes up from underneath and plugs into the vehicle, refueling it, much like how jumbo jets at the airports are refueled. A third approach could be pulling up next to a gas pump and a robot arm, much like those used in automated industrial manufacturing, locates my vehicle's refueling door, opens it, refuels my vehicle, and closes the door. For those two approaches, the driver may interact with the device much like a drive-through ATM machine at the bank for fuel selection and payment purposes. Speaking of, to build a better business case, perhaps we can provide ATM capabilities while it's refueling the vehicle. Transaction fees could help increase the return on investment for the gas station owner. This approach, however, doesn't technically meet my requirements in their entirety, since the driver has to roll down their window to access the machine, and that's okay. At this point, I was simply going over some of the different scenarios in my mind. After I've thought about these things, now's probably a good place to start the process and get things a bit organized. One of the first tools in your systems engineering toolbox is the concept of operation, or CONOPS. This will help you put the picture together for what your system will be doing and what it will be interacting with. It will also generate a list of inputs and outputs from those elements that it's interacting with as they relate to each significant phase of operation, on top of the system's life cycle. You will not complete and document your concept of operations until you're in the next phase, concept exploration, but you should still develop a high-level CONOPS to assist you during needs analysis. I won't take up time in these videos to go over step-by-step development of a CONOPS. Some good sources for developing a CONOPS include a review of the Intro to Systems Engineering and Design and Integration lectures that pertain to CONOPS, and also refer to the Charles Wasson SAD&D textbook, Chapter 18, which pertains to the system's operations model description. It goes a bit more into detail than Chapter 7 of SEP&P, which is yet another good source of information. Finally, another great source is the Dennis Beatty book in Section 6.10. As I have stated, none of these solutions are written in stone, and perhaps the ultimate solution at the end will not resemble any of these. We will let the systems engineering process drive that. The point here is simply to visualize the different ways to meet the initial need, assess the risks for each of those, and document these, as well as my findings, in the concept development report. I can do a little research and discover that some of these concepts are not feasible. For example, the heated garage may not be feasible since current federal gas station laws require refueling areas to be open to the atmosphere for ventilation and fire safety purposes. So the next step is to use the concept of operations to both determine what major stakeholders my system will be interacting with, the information that would be shared between them, as well as to define my system boundaries. There are a few criteria I could use to determine whether or not to include entities as a part of my system or external to my system. These are outlined in Chapter 3 of SEP&P, Chapters 2 and 6 of Dennis Beatty, and Chapter 11 of the Charles Wasson book, so I highly recommend taking a look at those chapters. One of the tools that can assist me in depicting the boundaries of my system is the context diagram. This effectively shows what external entities are interfacing with my system from a high level and what major interfaces are going into and out of my system for each of the entities. With the context diagram, my system is at the center of the diagram and nothing internal to it is being depicted. We simply want to be thinking about my system in the greater context, or the system as a whole, what my system is interfacing with, and what interfaces with my system. One of the first and most obvious interfaces is with the vehicle that I will be refueling. My system will be supplying fuel to it, while it will be providing its location and mere presence to me. The vehicle operator will interface with my system in that they will request fuel, perhaps withdraw money if an ATM option is provided, select fuel type, and so on. My system will provide a receipt, it will give them feedback for status of the refueling, and any information that needs to be passed along to them. My system will also interface with the gas station or gas station attendant. It will be tapping into the fuel supply and the physical gas station itself, such as the island it sits upon and overhead shelter it sits underneath. My system will be providing feedback to the fuel supply, as well as any indications of maintenance fault or maintenance required. One of the more obvious interfaces is with an external maintainer. My system will provide system status, expendables, fault codes if necessary, parts that need to be replaced, while the maintainer will provide services, new parts, and new materials. Something unique about this one as well is I have color-coded both the inputs and outputs blue. This means that the inputs and outputs to the maintainer belong to my system, and as the systems engineer for my system, I am responsible for both the inputs and outputs from the maintainer. One last interface I think I should be included is communication back and forth to the financial institution for approval of transactions, authorizations, ATM withdrawals, if applicable, etc. We could and should take a step deeper and think about alternative scenarios, such as someone attempting to hack into the ATM system, vandals trying to destroy the refueling system, or someone inadvertently driving away while the system is in use. This is beyond the scope of the minimum project requirement. However, if you would like to go above and beyond for your project to obtain a higher grade, feel free to do so. Now that I have my context diagram, I can derive some more operational objectives that I must consider for my system to meet the need. I perform my market research, interviews, and conduct high-level operational scenarios, and then begin building a hierarchy of operational objectives. Some rules of thumb for the operational objectives can be found on page 149 of SEP&P. Here's a hierarchy of my system from operations analysis. Basically, my top-level need has several lower-level operations that must be performed in order to meet it. Primarily, refueling vehicles without the operator having to exit the vehicle, operating in extreme environments or weather conditions, being safe, or in other words, complying with federal and local statutory and regulatory requirements, maximizing return on investment, being capable of interfacing with various payment methods and gas station infrastructure, as well as providing ATM services as an option. These alone are not enough to validate the need, as many of them are untestable, so I have to decompose them a little lower to come up with lower-level operational requirements. There are a few good bullet points about operational requirements on page 149 of your SEP&P book, but an even more detailed explanation can be found in paragraphs 6.9 through 6.12 of the Dennis Beatty book. What you're seeing here under my needs statement are operational level requirement titles and their lower level requirement titles. This graphic does not contain the requirement statements themselves. You'll also notice my needs statement is very high level and broad. It's as though a non-expert wrote this needs statement. That's how needs statements should be made, as they allow developers the flexibility to come up with various ideas to meet the need and minimize backing the systems engineer into a corner, forcing them down a path that may not be the best solution to meet the need. At this point, I'm going to go into core and input my operational requirements and create the hierarchy. So here's what core looks like when you open it up. I'm going to go ahead and go into the Model Assistant, make sure that autocreate root functions is unchecked. And then I'm going to use this Systems Engineering tab over here. This contains all of the elements that we'll be using most of the time when we develop our project. So the first thing I'm going to do is go in here under Requirement and input my need statement. I do this by either right-clicking inside here and clicking on New Element, and then I will go ahead and type in need statement, and there it is. So then I go in here and I type in exactly what I had previously for my need statement. So there's my need statement. I'm going to go down here to type, and I'm going to choose composite because this is a composite. Might as well go over what some of these are right now. Composite, that's an overall high-level requirement. Constraint requirement, self-explanatory. That's bounding basically your available options for the requirement. Functional requirements, incentive award fee criteria, but we won't be using it for this project. Performance requirement, when we get into concept exploration, we'll be developing a heck of a lot of performance requirements. Programmatic requirements, these kinds of things you'd find probably in a statement of work. Test requirements and verification requirements. So I'm going to go ahead and choose composite. Key performance parameters, since this is a need statement, I'm not going to mark this as a key performance parameter. My measures of performance, when I start to develop those may become key performance parameters when I actually start doing, when I actually perform concept exploration and come up with some of my performance parameters. Origin is originating, so we've got 3 here: derived, design decision, and originating. Most of these will be either originating or derived. The types of requirements that are originating are basically from the users or potential users, some of the major stakeholders, and of course, since this is a need statement, this is originating, so I'm going to click that. Paragraph number and title, well, I'm not going to use those because I'm not referencing any of these. And down here we've got our relationships. So when I create my child requirements or my lower level operational objectives, I go down here to refine by and I double click on that. That opens this field right here. If I double click requirement, then it creates a new requirement and I can name that requirement whatever my first operational objective may be. In this case, it's going to be autonomous refueling. And then I hit OK. And now that relationship is established, and if we take a look at the hierarchy from the need statement, we could see that the need statement is at the top and it's refined by the autonomous refueling. So let's go back to the need statement, and I'm using the tabs down here at the bottom to view that. Go to the tabs down here and go back to the properties and do this again for the next requirement. Double click on refine by, double click on requirement, and we'll type in safe. Do the same thing again, and we don't have to hit OK now, so instead we can just double click on it. Something that I should mention about the cost-effective requirement is that it is not going to be decomposed any lower for this project. We're going to use basically our armchair analysis or informal trade studies to come up with cost-effective, except for the ATM portion of this. So I'm going to decompose it probably 1 level down, and you saw that just a few minutes ago. So that's it. Here's our hierarchy. So now let's decompose this 1 more level down to make it look just like what I had a few minutes ago. So now we're going to go into the individual requirements, autonomous refueling right here. And then I'm going to do refine by again. Remember, we're going from the top down. So refine by, and then I'm going to double click. And then hit OK. And then take another look at my hierarchy. First, we've got to click on the need statement. Otherwise, let me show you real quick. It's going to show the hierarchy of just autonomous refueling. And that's what it looks like, which is fine. But we want to go 1 level higher to the need. So let's click on the need statement. And now we can see that the hierarchy is decomposed 2 levels down now. So let's go ahead and go back and do this for safe next. To save you from being bored, I went ahead and paused the video. And now here's what we're looking at. If we click on the need statement, let me find it in the list here, and then click the hierarchy. So here's what the diagram looks like now from the point of view of the need statement. We've decomposed a couple of them, safe and autonomous refueling. If when you look at this diagram initially and it looks like a mess, just go up here to this little box up here, set the layout for the diagram, and select any one of them, like hanging. Select any one of the different ones right here like this. Choose the best one that you like. This one looks good. This one looks a lot like the chart that I had a few minutes ago. So I'm going to go ahead and keep it on this one. We started out on vertical right here. My original point was when you click on this, it straightens everything out. So if things are messed up and kind of meshed together a little bit like this and kind of messy, and when you click on this diagram, just go up here and click on any one of these and it'll straighten things back out. See that? So now I'm going to pause the video again and go ahead and finish doing the other subordinate child requirements underneath my operational objective. So now I've completed doing that. Now let's go back to the needs statement, and here it is. Look at the hierarchy for that. And it is a big, long hierarchy. It goes on for days, and it's only 2 levels down. So how do we fix this? Like I said, so we go up here and let's do the organization chart format, and that cleans things up quite a bit. It kind of brings things in to be more narrow. And another trick with this chart is we can resize things according to how big the text is inside of each one of these boxes. So I'm going to go ahead and hit Control A or select all and go up to this little bar up here and do auto size the nodes, and then I'm going to do auto size icon height. There you go. And it kind of narrows things down a little bit more according to how big their text boxes are. So one more thing that we need to do is go ahead and number these, and the way the numbering works in Core is you assign basically this scheme for numbering way up at the top, up here at the need statement. And there could be one or more need statements for your project. There's only one for mine, so I'm going to go ahead and go in here and start the whole process off by just calling it R.1. If there were more than one, then it would be R.2 would be the second need statement, and so on. So this is how it starts, and then we right-click on it, and we do renumber element. New number, since it's not in there, let's do R.1 again. There's a drop-down here that you could select different types, alphabetic by class, and so on, but we're going to keep it numeric by class. The way this works is, since it's by class, everything underneath it will be auto-assigned a number accordingly. And so we'll go ahead and hit OK. And there we have our numbering scheme set up according to our hierarchy. For example, R.1 here, 1.1 autonomous refueling, and then 1.1.1, and so on and so forth. So you can look through this and see exactly how the numbering scheme works all the way to 1.6. So that's pretty easy and convenient way to renumber elements in Core. And if you go ahead and change and swap requirements around, let's say you move this child over into this parent, best way to renumber things instead of typing it back in is to go all the way up to the need statement again and do the exact same thing again. Do renumber element, start it at R.1, or you can even do R. And it'll renumber those things accordingly. So now it's a little bit cleaner, R.1, .2, and so on and so forth. When the operational requirements are decomposed to a level that you begin to define how the requirements will actually be met on a functional level, is the transition from operations analysis into functional analysis. It's here that we will translate these operational objectives into functions and then visualize potential subsystems that can currently perform these functions or that may require some engineering. In order to correctly perform functional analysis, you must continuously keep your mind in check when creating functions, to avoid going down a path that may not be feasible in the end. If you're not an expert in the field for the system you're conceptualizing, you'll be required to conduct thorough market research and interviews to ensure the path you're following is realistic and feasible. When conducting functional analysis during the needs analysis phase, it's best to keep your functions at a high level. Decompose them only until you're confident that you have correctly identified either pre-existing technology or technology that will require engineering in order to perform these functions. The purpose here is not to dive deeply into how the system will actually operate, only to flush out high-risk technologies and feasibility for your system. When performing functional analysis, it's important not only to focus on the primary mission of the system, but the entire system lifecycle should also be considered. Most of the functions I have identified focus on the refueling portion of my operational requirements. This is the area that will require the most market research and high-risk technologies, so my primary functions include the fact that my system should be able to detect the presence of the vehicle to start the refueling process, find the location of the vehicle in space, and more specifically the location of the vehicle's refueling port, It must be capable of opening the refueling door, removing the cap, inserting the fuel nozzle, and refueling the vehicle. It must be able to retain the fueling cap, stop refueling once it's reached its limit command, relocate and secure the cap, close the door, move away from the vehicle, and finalize the transaction. One final point for this is, it must perform all these functions without damaging or so much as scratching the vehicle it's interacting with. This is in and of itself a higher risk. Some of the other functions are lower risk, so they're not decomposed to that level. An example being interfacing with the driver. This can be met by some type of drive-up style ATM machine that doesn't necessarily require further decomposition at this point. We cannot declare functional analysis complete until we identify the interfaces between these functions, as this is where the greatest risk lies during development of any system. Included in this list of interfaces are the interfaces with those external elements we identified in our context diagram. One rule of thumb I like to keep in mind for the functional interfaces is that they should be expressed in terms of the acronym FEDS-M: Forces, Energy, Data, Signals, and Materials. We saw this in the context diagram towards the beginning of this video. They should not be expressed in physical interface terms, such as wiring, hardware mounting provisions, or brackets. These are physical interfaces, and some might argue hardware configuration items in and of themselves, but we won't get into that discussion during needs analysis. Here's how to input the functions and the functional interfaces into core. For functional analysis during needs analysis, we start with the requirement, and we work in a top-down fashion. So we start with the top requirement, and then we create functions that need to be performed in order to meet that requirement. So starting all the way at the very top, we need to come up with a function or a functional statement for the need statement. I feel that the lower level functions better answer the need statement than does a single top level function. Therefore, I'm going to generalize the top level function to simply performing AGP functions. So now let's create our first function. We do this by double-clicking on the basis of relationship here. And we see that there are 4 target classes that we can point to from the requirement. One of them is a function, and that's what we'll be using. Another is a program activity. Another is a use case, and another is a verification requirement. So let's double-click function, and then type in perform AGP functions. Now let's go down this list of requirements and come up with associated functions for each one of these requirements, if applicable. So for autonomous refueling, we need to come up with an associated function for that. Double-click on basis of, double-click on function, and let's write in provide autonomous refueling. I'll go ahead and go down this entire list and create functions associated with each one of these requirements. So now I've gone through this list of requirements and I've assigned associated functions with each of these where applicable. Some of them did not have applicable functions since they were constraints on the design of the system itself, such as regulation compliance, maintenance, reliability, maintainability, size, weight, and shape, and so on. So now what we do is we take a look at our functions. Here's our list of functions, and each is traced back to their associated requirements. But they are not in any kind of hierarchical order. Each one exists on its own, floating out there in functional analysis space, if you will. So now we just need to create a hierarchy with this list of functions, and we do this the same way we did with our requirements, which is we pretty much follow the same format that the requirements are in, or whatever makes the most sense. So we start with the need statement associated function, and that one is at the top, which is perform AGP functions. It's based on that need statement, and it's decomposed by all of the children functions. So we start at the top here with perform AGP functions, and it's first decomposed by the autonomous refueling function, which is right here. So let's go up to perform AGP functions, and this is decomposed by, we'll double click that, and then we will find perform autonomous refueling, which is right here, double click that. It's also decomposed by providing ATM capability, providing ease of use, operating in extreme weather, perform using existing payment system, operate on existing gas station islands, and perform safely. So if we take a look at the hierarchy now, we can see it's starting to form up. But now we've got some of these underneath these children functions that we need to assign as well, such as all of the extreme weather associated functions. Let's do that now. So we're going to go to Operate in Extreme Weather. We'll go to the Properties sheet again, Operate in Extreme Weather, right here. And this is decomposed by. Now we're going to choose all of the different environments that it has to operate in. We'll click Add, and we accidentally included the parent on this one, so we need to take out Operate in Extreme Weather right here, and then click Add, and then click OK. So now let's take a second look at that hierarchy again, Perform AGP Functions. So now we're looking 3 levels down. See how this is starting to form? So let's continue. Let's go to the Autonomous Refueling. Provide autonomous refueling here, and it's made up of several different subfunctions. Decomposed by, interfacing with customer, gas stations, vehicles, provide service for various transaction types, and provide service with various fuel types. Let's take another look at the hierarchy. So we can see it's really starting to build now. Let's continue. Okay, I put it on pause and did that same thing for the rest of the functional architecture. So now we have a complete hierarchy of my functions, and they're all traced back to requirements. So now in the video, we also showed you a list of functions that my system should perform at one level deeper that aren't necessarily traced back to requirements, but are traced back to a parent function. This function that are traced back to a few parent functions. These functions are interfacing with the vehicle, interfacing with the driver, and operating safely. So we'll go ahead and do that now. So we're going to choose Interface with the Vehicles, Properties dialog, and we'll decompose that one. And now we'll start creating the functions associated with that, just by double-clicking and typing them all out. So now we've got these lower level functions associated with interfacing with the vehicle. There were a couple other ones that had to do with interfacing with the driver. So I'll go ahead and decompose those as well. Actually, there only ended up being one. So let's take a look now at our hierarchy and see what it looks like. So we can only see 3 levels down in the hierarchy. But Core is letting us know that there's something going on deeper inside of a couple of these by putting this little black box in the upper left-hand corner of the functions that have lower-level functions inside of them. If we want these lower-level functions to show up on this high-level hierarchy, all we have to do is right-click and go down here to View, go to Local Diagram Options, and where it says Levels right here, we're going to choose 4 since we only have 4 levels to show, and hit OK. And there we have a look at the 4 levels of our functional decomposition. The issue I have with this hierarchy is it spans across quite a wide range, and it would be very difficult to put this on your functional analysis report. So what we're going to do is go up here and select Organization Chart Format, and that kind of lays things out a little bit neater format, although it is still kind of tall. So we'll split it among different pages if we have to. At the end of the day, when you have your entire functional architecture, you're not going to be able to put it on a single piece of paper anyway. So you're going to have to pick and choose what you want to display. So now that we have our hierarchy figured out, the next thing we need to do is come up with our functional flow for these functions. Now, we could just go to the Enhanced Functional Flow block diagram, but I want to show you how to include or exclude certain types of diagrams. The difference between the Enhanced Functional Flow block diagram and the regular functional flow block diagram is that the enhanced functional flow block diagram has the inputs and outputs displayed on the diagram itself. Now, if you want to show the diagram itself in an uncluttered fashion, you want to use the regular functional flow block diagram, but we don't see that as a tab down here, nor do we see it as an option up here at the top. Now, the way that we can display that is we can go up here to this downward pointing arrow and go to our toolbar editor, and scroll down this list until you find functional flow block diagram. It's probably abbreviated here, FFBD. So there's EFFBD. We want to go to, here it is. So here's functional flow block diagram. Now over here in the contents where we want that to be found is we're going to click and drag where we want it to end up. And we want it to end up here with these guys up here, probably right next to the enhanced functional flow block diagram symbol right here. So we'll scroll down until we find that. And we're getting close. There's the enhanced functional flow block diagram. So we'll click and drag this and put it right underneath that. And then hit OK. But that still doesn't give us our tab down here at the bottom. So to get the tab to show up, we're going to go up here to Tools, go to User Preferences, and then right here we have Project Explorer Diagram tabs. So we can click and unclick the tabs that we do and don't want. Personally, I don't use the spider. I don't use the package. Use case I'm not going to use right now anyway. Structure block can go away. Classification can go away. Interface n squared and block can go away. Internal block will keep. Physical n squared can go away. Physical block will keep. Flow internal we can keep. State transition will take away. There's functional flow block diagram. So we'll check that. It was unchecked before. And there's enhanced. There's activity. We'll take activity away. Sequence diagram, we'll take that off. And IDEF0 we're going to take off. However, after we clicked OK, they still didn't update. Well, let me show you something. That's because changes on the Project Explorer tabs will take effect the next time you open a Project Explorer. So all we have to do there is go up here to this table, and that takes us out of the Explorer view, and then click back over here to the Explorer view once again, and we should see our, let's just click on any one of these random functions, and we should see the tabs that we wanted down here at the bottom. So there they are. Instead of having to restart core, we could just switch it over that way. So back to what we were doing. We were on the functional flow block diagram for performing AGP functions. Inside of our functional flow block diagram, we can see this series of child functions are being performed in series with one another. That means after I provide autonomous refueling, then I can provide ATM services. Once I'm done providing ATM services, then I can provide ease of use and so on along down the line. This is not how my system operates. In fact, my system performs all of these functions all pretty much at the same time. So what I need to do is I need to generate an AND logic inside of this diagram and put all of these on that AND logic. And there's a lot of different ways of doing that. Just to go around the border of this diagram here, on the right side we've got this parallel. We can click and drag. By default it's set to 2 branches, so if we drag it in there we've got 2 branches. Or this one here, we can click that, and now we can choose how many branches we have. We can select 9, and now it shows up at the tail end of it. There it is, all the way at the tail end. And we can delete it by simply clicking on the AND word and then hitting our delete key. We can also go up here to Diagram, Insert, another AND right here. So let's do it that way. So now we've got 9 branches on here. So what I'm going to do is go all the way to the edge of this, select it, and hit Control X. That cuts it. And now we're going to go to the front, select the first one, and hit Control V or paste, and there it is right there. So now we need to get each one of these boxes on each one of these lines here, and it's a little bit slow and arduous, but once you do it you don't have to do it anymore. So we'll hit Control X to cut, hit Control V to paste, and we do that on down the line until all 9 of these are on each one of the lines. And it looks like I accidentally left one off. The way we correct that is we select this AND word right here. We right click and we select Insert and then Branch. And we just insert one more branch on there. Insert Position at the top or the bottom, it really doesn't matter. And I believe it's at the bottom, so now Control X, and here we are at the bottom. So this is our functional flow block diagram for the high-level perform AGP functions. There are some child functions that we need to break down. Perform safety only has one underneath it. So let's go to provide autonomous refueling. This one has a little bit more complexity to it. So before we do that, I think now is probably a good time to number these elements. And it's incredibly easy. Let's right click, renumber element, and then just put F dot right here for all the functions. And leave this as underscore follow decomposition. Hit OK. And now all of our functions that have relationships with something else are renumbered. And we can see that there's a function right here that's not tied to anything. So let's go through here and tie that to what it needs to be tied to. This is tied to the high level decomposes provide AGP functions right here. And then we go up here, right click, renumber elements, keep it on F, hit OK, and now it's got its own number. Now that those are numbered, let's get back to what we were doing with providing autonomous refueling. I'll click on that and then click on the functional flow block diagram. And now we've got several different things that also need to be happening concurrently as well. So let's go ahead and create the AND branch again, a different way this time. Let's click this one and do 9, not 9. 1, 2, 3, 4, 5. It's 5. Do the same thing, Control X and Control V. I also decomposed the interface with vehicles piece a bit, and this is a little bit different. This one is not all in parallel. This one has a little bit of both elements to it. So let's see how we can do that here. First of all, we need to arrange this series of functions into the correct order. We do this the same way we've been doing it the entire time. First step is to detect the vehicle, refueling door, open it, remove the cap. Looks like everything's in order so far. Insert the fuel nozzle, refuel the vehicle, retain it. So retaining the fuel cap is one of the functions that needs to be performed alongside several of the other ones. It needs to retain the fuel cap once it is removed all the way until it is secured here. So these middle activities in between need to be put in parallel order with retaining the fuel cap. The way we do that is we're going to insert an AND before insert fuel nozzle. Right after we remove the fuel cap, we're going to retain it and perform these three functions at the same time. And we'll do that this way instead this time. So we'll go ahead and put a second one in there. And we'll just do the same method as before. Insert fuel nozzle. This goes up here on the top, Control V. Refuel the vehicle, Control X, Control V. Looks like it's a little out of order, so we'll fix that later. Retain the fuel cap. This is the one that happens at the same time, so this is going to go on the bottom branch. Stop refueling, Control X, Control V. Relocate the cap, Control X, Control V. And then secure the cap happens after all those things. But they don't happen in this order, so insert the fuel nozzle goes up here in front of refuel vehicle, Control X, select that, Control V. Insert the nozzle, then refuel, then stop refueling, and then relocate the cap, and then secure it. So that's the normal mode of operation there. And then once it's secure, you're going to close the door. Those are the high-level functions for interfacing with the vehicles. And the reason why we decomposed it this low, just for this one area, is because, as we discussed previously, we want to take a look at the higher risk areas and identify those areas that will require new technologies or some research and development in order to mature technology in order to perform these particular functions. And we can resize this chart a little bit by removing that, clicking on this hourglass here, going to 75%. We can see it a little bit better this way. So now that we have a draft of the initial functional model, now we need to identify the inputs and outputs, both from external systems and within our own system that we need our system to react to. How we do that in core is through the element items, which is right here. Now we create items and we link these together with different functions. For the purposes of this demonstration, I'm only going to show you how to do the items associated with the interfacing with the vehicles functions. So taking a look at our concept of operations, or what we've thought about for our concept of operations, a vehicle pulls up next to the gas pump, and we could autonomously begin the operation, but we probably don't because maybe the person doesn't necessarily want to start the operation right away. So what we'll do instead is wait for the user to command the AGP system to start. So this detect vehicle function, the name should actually change to start the sequence or something like that. I'll go ahead and do that now by right-clicking and renaming the element this way. Let's switch over to the enhanced functional flow block diagram to give us a better view of the inputs and outputs of these functions. Now, there are several ways of doing this, but I think the easiest and quickest way of doing it is to stay on the enhanced functional flow block diagram the entire time. So what you do is you select it, you right-click on it, and you select Data, Edit Inputs, and that goes directly to items. So now we're going to create an item by double-clicking on it, typing in sequence start command or something like that. And we say signal because it's one of the elements of the FEDS-M acronym. So this is the S in FEDS-M, signals. Start command signal. Now the start command signal is the input to this, and the output of this, so we want to initiate the refueling of the vehicle, and the output is refueling of vehicle initiation complete. So we go down here to data and edit the outputs. So there's that. So now we have an item that is an input and an output from a function, which is required in order to say that something is a function. A function can't exist all by itself without an input and an output. Every single function in the entire world, at least according to systems engineering, always has an input and always has an output. So this output serves as the input to this next one. How do we make that connection? We go to the next one and we right-click, go to Data, Edit Inputs, and now we select from the list here the item. And there it is. There's that connection. We can select all and clean things up a bit. Auto size, icon height. There we go. So now we can read everything. So I'm going to go through here and complete this process for the rest of these functions. So here's a quick run-through of what I've just done. I've gone through all of these functions and created items or inputs and outputs to each one of these things. Now, why did I do all that all the way in the very beginning under needs analysis? So I go back to the conversation about functional analysis and identifying high-risk areas, visualizing subsystems. Well, interfaces also drive various pieces of hardware. For example, let's take a look at the fuel cap retain confirmation signal right here. This is an output from this. All of these signals, actually, they are driving the need to have some kind of a pressure sensor of some kind installed that can detect whether or not the refuel door is open or closed, or if the cap is off or on, or if it's actually retained, or if it's fallen off of the apparatus that's holding on to it, and what have you. So all of these things are driving different pieces of technology and hardware, and it's very important to identify those things all the way up front in needs analysis so that you can get a grasp of the level of risk you are approaching when you start to develop your architecture in the future. So that's why we did that for this. Now, I'm going to go ahead and pretend I did this for the rest of my architecting right here. You'll go ahead and have to do that on your projects. One thing that I didn't show you was the link between what's in my context diagram and what's going on inside here. So make sure when you do your projects, you take into account all of the inputs and outputs from your context diagram into the top level functionality. So before we move on, we just want to touch on the n-squared diagram a little bit here. So taking a look at the n-squared diagram, we can see all of the child functions within my interface with vehicles parent. One of the things that you'll notice is that this is a very tightly bound n-squared diagram, and what that means is all of the inputs and outputs associated with the child functions in here are related to each other. An input from one is an output from another, and so on. There are a few exceptions. Coming in from the top, we've got 2 external inputs and 1 external output going over to the side. One of the things that's very important for us to do is make sure that the parent is also covered. So the parent should have these 2 as an input and this as an output as well. So we'll go ahead, and I know that connection has not been made, so we'll go ahead and make that connection now. So it's easiest just to stay on the n-squared diagram when we do that, just to keep things in order and we don't get lost going down weeds. So let's stay on this n-squared diagram. We're going to right-click on this. We're going to go to Open Element Properties for that particular input. Down here in the relationships, let me drag this up, we're going to go input to, and we see the child that it's an input to, but it needs to be an input to the parent as well, into the interface with vehicles. The start command signal is not given from the interface with vehicles, it's given from the interface with the customer. So we'll do the input to, and we'll go to the interface with vehicles. Make that connection, and while we're here we can do output from interface with customer. And here's a second one, and we do the same thing with this one. Open the properties, go to input to, go to interface with vehicles, output from. Refuel limit signal is given from the interface with the customer. So he tells us either by the amount of money they put in or pushing of buttons the limit, how many gallons they want in their tank, or telling it to fill up all the way. So that signal is given to the interface with vehicles functions. Now let's go to the output over here and right click on that. Open element properties, same thing, output from, and we'll do the parent. Interface with vehicles. That confirmed signal tells other things what to do. The door close confirmation signal is an input to finalizing the transaction, and the finalizing of the transaction is inside of the interface with customer, so we've got this and that as inputs. The cleaner and neater way this would have gone is I would have started with interfacing with vehicles and identified based on my CONOPS what those input and output signals should be and then decompose from there, but I didn't do that this time. So it's good practice to do it that way. One more area we need to take care of before we proceed is including all of the information from our context diagram into our architecture. So what I have to do in Core is, since these are all physical things right here, is translate each one of these physical things into a function first, and then input their interfaces with my system into Core as well, using the items. So let's go ahead and do that now. One of the first ones that I should probably put in there is the vehicle. Now the vehicle is an external system, so we can actually create the component and then go backwards and create the function. That might be a little bit easier, but for the sake of showing you how to use Core, I'm just going to keep it on the function instead. So we'll right click in here, new element, now that we have these external systems represented in the functional area, these are at the same level as my perform AGP functions. So we should see these interfacing with my AGP at a higher level. In order to do that, I need to create yet another function that's above perform AGP functions and call it the AGP context. So I just recorded a whole session without the microphone being on. And what I did during that session was I took the inputs and outputs from the AGP context from the externals in the context diagram, which is right here. And I took all of these inputs and outputs and I put them into core, and you saw me do that. And then what I did next is you could see the properties right here, all the inputs are what we were looking at before. So then what I did was I went in the n-squared diagram right here and I accounted for each and every one of those. So let me just enlarge it a little bit so you can see it. And I did that by right-clicking on each one and clicking on data, editing inputs, and putting the appropriate inputs in there. These are the same inputs we have coming in from our externals in our context diagram. So I accounted for each and every one of those. And you'll notice that there are some blanks. There aren't any functions that are being accounted for. And that's fine during needs analysis. So these are areas that we don't necessarily see high risks or where we need to do some research, find out what technologies are out there, what technologies need to be developed to perform these functions. The purpose, remember, was to identify those things for these particular functions. And I've gone a little bit above and beyond for the purposes of needs analysis, but I think covering all your bases in the very beginning, accounting for those inputs and outputs from your context diagram from the very beginning will identify and glean any of those areas that you need to come up with answers for, either developing a new technology, advancing a new technology, or incorporating an existing technology into your system. So that's how this can help you. And this is also the top-down approach. We're taking our inputs from our externals and we're converting those into outputs back to those externals. One final thing we should do is we should do some traceability back to requirements just to make sure we covered our bases. We do that through this little table view up here at the top. We're going to click on that, and here we can see our traceability. Here's the number, here's the name. Now we can go ahead and click and drag these. Description, we don't have that in there yet. Inputs and outputs and triggered by. So we're not going to be using triggered by or the description for the traceability right now. So we're going to right click up here at the top and do edit columns. Double click on description and triggered by. But we do want to include based on relationship as well as decomposes and decompose by. And that shows traceability. Shows your inputs, your outputs based on, decomposes, and decompose by for your complete traceability. Now you're going to be looking at blanks and asking yourself to fill in those gaps there. So that's it as far as performing functional analysis in core, at least from a needs analysis perspective. Let's continue our systems engineering discussion. It is at this point I'm going to allocate the refueling functions into a refueling subsystem and the driver interface functions to a driver interface subsystem. For the refueling subsystem, I have to ask myself what technology exists out there that can perform each one of these functions. Can a robot arm by itself perform all these functions? Could a drive-through style setup work for this? Perhaps one machine can open the door and another moves into position and opens the cap, and so on. The point is not to define a definite solution, nor to decide which one is better than the other, only to identify that there are existing technologies that can be tailored or used to perform these functions, or identify those functions that may require some research and development of some new technology to insert. These are risk areas that will require more focus during the next phase, which is concept exploration. Talk to an expert in this field if you're not an expert yourself, to help you identify some of these areas that will require a deeper dive. Make sure that if a technology does exist, that it can be applied to the operational conditions of your system. As I stated before, oftentimes a new technology or an existing technology is only used in specific and controlled types of environments. For example, robot arms were designed and developed specifically for manufacturing environments, most of the time in clean environments. If they were in extreme environments, they may require higher amounts of maintenance and replacement, and are often outfitted with additional protections from these extreme environments. The purpose of my system is to operate most of the time in environments such as this, since these kinds of environments are what will drive the desire for the vehicle operators to remain in their vehicles. Therefore, I will identify that these environments require particular attention to the operation of my system. Another example A drive-through style scenario sounds a bit more feasible for operating in extreme environments, but after some research and investigation, will require a lot more setup and equipment in order to operate compared with something like a robot arm. The same kind of thought was applied for the other concepts I've identified to meet the need. For the driver interface subsystem, I have to ask myself the same questions. However, they can be answered more easily by existing technologies with a little bit of software development. Some of the high-risk elements of this subsystem are the interfaces with the refueling subsystem. As with the refueling subsystem, we will identify the interfacing elements here as well. Once I have refined my concept in terms of operational objectives, identify the critical functions that the system will perform, and allocated those critical functions to components that either currently exist or require research and development to perform them, I document all of these findings in my concept paper and my proposal. Focus should be on the operational objectives. Functions and potential subsystems that were identified as critical to the operation of this concept should be included as well. For my project, the primary focus was on the interface between the vehicle and the gas pump. I did not identify that this would be a robot arm or a drive-through garage or some other concept. At this point, my system is yet to be defined, but I've identified the critical functions to meet my operational objectives and have identified potential components that may perform these functions or that may require some research and development. I did apply some thought and focus on the driver interface subsystem, and we identified that the functions this subsystem will be performing currently exist in the market and should only require a little bit of software development to interface with the refueling subsystem and the other stakeholders I identified in my context diagram. Let's finish things off in core on the physical side. We're going to go to the components area up here. Here we've got the system context component, which is already set up for us from the beginning. So that's great. One less thing for us to do. So now let's just go in here and create the AGP system itself. And then, following the same guidelines we did for the functional analysis, let's include all of the externals. Once we have the externals identified, we can go in and categorize them by externals. Now we've chosen system from our AGP system. Now let's create the context relationship or the context hierarchy. Click on System Context, and now the system context is built from relationship. So double-click Built From, and then Shift select all of the items, add them, click OK, and then go to the physical block diagram, and there we see them. We can resize them using this, or we could just select it and use this. We can also move these elements around. So let's put the AGP system in the center and make it look like our context diagram. And now we need to create those physical connections between my AGP system and each one of the external elements. And we do this by right-clicking on AGP system and clicking Edit Connections. And then we go in here, select this, select the link for the target classes, and then click on New, and that will create a new link. And we're going to link each one of these components together with the AGP system. So we'll call this one AGP-environment link. Now we need to connect the other end of this to the environment, so we go up to Environment, right-click, Edit Connections, click on Links here, double-click on the possible targets, and now we have our connection between the two systems, the environment and the AGP system. Now I'll go ahead and go through and do that for the remainder of these. Now we just need to clean up this chart, and how you do that is you click on this line right here, and this little black box at the bottom can be used as a handle to move this around. So let's move that and just clean up this area. So that looks pretty good. I'm a perfectionist, so I'm going to center that. One last thing we need to do is we need to create a relationship between these links between these and the information that's being flowed back and forth across these. So we do that by right-clicking on them, opening Element Properties, and then clicking on Transfers Relationship. And now we have a list of all of the items in our database, and we need to put all of the items that this is transferring. So this is between the AGP and the environment. So each one of these elements here from our context diagram is included on this. So now this link, the AGP environment link, is transferring all of these items back and forth across it, and they must be taken into account on the physical side as well. So I'll just go through the rest of these and complete this physical piece of the architecture. Now that we have this set up, we need to go one level deeper inside of the AGP system and break this down to just those two subsystems I identified earlier. And make the appropriate connections between them the same way I did before with the context diagram. I will also right-click on the context and renumber this element. We will call them components, or C, and there's our numbering system. So what we're doing here during needs analysis is simply setting up the foundation for our architecting for the next phase, which is concept exploration. And we are making sure that the interfaces between the externals and our system have been accounted for. Let's get back to our discussion on systems engineering for needs. One remaining step for needs analysis is to actually validate that the need can be met by what we have discussed so far. The book describes an operational effectiveness model, whereby we can look at an existing technologies and assess their implementation and how well they will perform in the operational environment for my system. Will a robot arm or a drive-through style setup perform with a high degree of reliability and speed in order to compete with the desire for a driver to step out into undesirable conditions to refuel their vehicle? Will a refueling device that comes up from the ground interface with existing vehicles, or will it require a vehicle to be outfitted with a special piece of hardware in order to interface with my system? How quickly can each of these concepts perform their particular functions? Can they do them fast or faster than the driver exits the vehicle to refuel? If not, will the folks that I interviewed accept that it may take a bit longer to perform the refueling while they wait in their vehicle? For most of them, it was worth the wait, but this only goes so far. So I'll still need to identify some performance parameters around the cycle time for refueling operations. From these types of questions, I will formulate my measures of effectiveness and measures of performance. At this point, most of my metrics will be measures of effectiveness, since I should not be decomposing my system into anything lower than subsystems. Otherwise, I would be steering the design towards a robot arm or a drive-through garage style setup, and I don't want to do that at this point. I can, however, define measures of performance for each of the subsystems. From this effectiveness analysis, I will determine whether or not my concept is usable and can potentially satisfy those operational objectives I identified from requirements analysis and ultimately ask myself if my concept can meet the initial need. For my system, I've done the work required and have identified those areas that require focus in the preceding phases, and ultimately, I have validated that there exists one or more concept that will meet the initial need. Finally, I apply all the work I've described up to this point to the initial set of operational objectives and translate those into operational requirements. Without having to take too much time explaining how to write good requirements, first refer to Chapter 6 in SEP&P. Now take a look at some of the basic components of operational scenarios that will help you identify operational requirements, specifically on page 159. As explained, I will also include system-level requirements that are essential for the development, transportation, setup, operation, maintenance, and ultimately the disposal of my system. One critical point for requirements here is that your requirements should be describing the performance of your system as a whole and should not be describing the performance of any one particular part of your system, such as how well a robot arm should perform, or how well the ATM should interface with the driver, or what types of payment should be accepted. Treat your system as one big box and describe its performance at this level. As I'm developing these requirements, I'm inserting them into core and creating their relevant relationships with higher level requirements. We've done a lot of work up to this point, but it will all pay off with the rest of your deliverables. As you have already developed your foundation for your requirements analysis report, for your functional analysis report, you've even identified the foundation for your concept design report. Some of what we talked about, and in particular what you have entered into core, will not be included in your concept report or your proposal, but they were required in order for you to validate your initial need and describe your concept with a good amount of confidence. If you would like specific details on producing an outstanding concept paper and proposal, please refer to the project guidelines as well as Steve Beamer's office hours videos on the Final Project 800 site through the path shown here. I also demonstrated how to get there in my previous video. Congratulations, you've completed needs analysis and you've performed the systems engineering process at least one time through. You may need to return to needs analysis if your concept paper or proposal are rejected for unsound concepts. This is the arrow we see pointing back to the beginning of the phase. Don't be disheartened if this happens to you, as this is a critical piece of performing systems engineering correctly. In order to develop a system that provides value to the stakeholders, you will need to refine your concept until you can do so. This refinement is achieved by iteratively performing the systems engineering process on top of approaching the concept from a top-down perspective. In the next video, I'll be using the outputs from the needs analysis phase as the inputs to concept exploration, and maturing my project to end up with the performance specification and candidate concepts as the output. We'll see you then.